everyone. In the previous class, we discussed about calculation sequence for a rock mass tunnel support interaction analysis using the method proposed by Ladani. So, we will continue that discussion today as well. We saw that there are 6 different steps which are involved, out of which 2 we already discussed, that is required support line for the rock mass and also the support stiffness and maximum support pressure for concrete or shotcrete lining. So, today we will cover remaining 4 aspects which are the support stiffness and maximum support pressure for blocked steel sets, then support stiffness and maximum support pressure for ungrouted mechanically or chemically anchored rock bolts or cables, followed by the available support curve for a single support system, and then in case if the requirement is such that more than one type of support system is needed for a single application, then we should know how to determine the available support curve for such a case. So, here we will be taking up this that is the available support curve for a combined support system. So, to start with, let us have our discussion on the determination of support stiffness and maximum support pressure for blocked steel sets. Like we did in case of the shotcrete, here also we need to provide the input data. So, let us see what all are the data that is required for us to complete this particular step of the calculation sequence. The first input data that is needed is W, which is capital W. Here we are representing this for the flange width of steel set. Then we have capital X, which is depth of the section of steel set. Next is AS, which is the cross sectional area of steel set. Then we have IS, which is the moment of inertia of steel section. Next is sigma ys. This is yield strength of steel, and we have Ri, which is tunnel radius. So, these are some of the data. Along with these, further we would need S, which is the steel set spacing along the axis of the tunnel. Then we have theta, which is half angle between blocking points. Keep this in mind that this should be in radians. Then we have TB, which is the thickness of block. And finally, we would need EB, which is the modulus of elasticity of the block material. Now, having these data with us, we are ready to calculate now the support stiffness and maximum support pressure for blocked steel sets. We have already discussed that what exactly are these expressions, but here we are putting together all the things at one place. So, we have here support stiffness and the maximum support pressure as the first step will be with respect to the support stiffness, which is 1 upon Ks is equal to S into Ri divided by Es into As plus S into Ri cube divided by Es into Is in bracket theta into theta plus sin theta cos theta divided by 2 sin square theta minus 1 plus 2 into S into theta into TB divided by EB into W square. So, this is how the support stiffness can be determined for the blocked steel sets. How about the maximum support pressure? That is going to be PS max equal to 3 ASIS into sigma YS divided by 2 into S into RI theta in bracket 3 IS plus X times AS into RI minus TB plus half of X, this bracket closed, multiplied by 1 minus cos theta. And this is going to be the completion of this box bracket. So, this is how we can determine the maximum support pressure and the support stiffness for blocked steel sets. Let us go to the fourth step of this calculation sequence for the analysis. So, here we deal with the support stiffness and maximum support pressure for ungrouted mechanically or chemically anchored rock bolts or cables. So, as usual, as we did in the case of shotcrete and the blocked steel sets, we will need the input data for the determination of support stiffness and the maximum support pressure for ungrouted rock bolts. So, let us take a look at what all data that we need. The first one is small l, which is the free bolt or cable length. Then we have dB, which is the bolt diameter or equivalent cable diameter. We have EB, which is the elastic modulus of bolt or cable material. Then we have capital Q, which is the load deformation constant for anchor and head. Further, we would need TBF, which is the ultimate failure load from pull out tests. And in the previous class you have seen that how the typical result from the pull-out test with reference to ungrouted mechanically or chemically anchored rock bolts look like, and how we can determine this TBF from that test result. Ri as usual is the tunnel radius. We have SC as the circumferential bolt spacing, and SL, that is longitudinal bolt spacing. If you recall our discussion, so if this is the circular tunnel, so this is how, if these are the directions in which the bolts are installed, then this circumferential distance center to center, this is SC, and SL is going to be the spacing of the bolts in the direction perpendicular to the plane of screen, which is the spacing along the length of the tunnel, or we call it as longitudinal bolt spacing. So, the next step after knowing all this input data, the next step is going to be the determination of support stiffness and the maximum support pressure. So, let us write those expressions here. So, for the support stiffness, we have 1 upon Ks is equal to Sc into Sl divided by Ri in bracket 4L divided by pi dB square into Eb plus Q. And we have the maximum support pressure as Ps max, this is equal to TBF upon Sc into Sl. So, using these two expressions, we can respectively find out the support stiffness and maximum support pressure in case of an ungrouted mechanically or chemically anchored rock bolts or the cable. So, now we take a look that how should we determine the available support curve for a single support system. So, for that, what is the input data that is needed? Let us first take a look at that. So, here we will need the K, which is the stiffness of the support system under consideration. Then we will need Ps max, which is the maximum support pressure which can be accommodated for that support system which we are considering here. Then we will need UIO, which is the initial tunnel deformation before the installation of the support system. So, what is going to be the available support curve? So, we will have here as available support curve will be that in case if you have for Pi less than PS max. This is going to be Ui upon Ri is equal to Uio upon Ri plus Pi upon K. So, this is how we will be able to obtain the available support curve in case of the single support system. Now, this single support system, it can be maybe the shotcrete or blocked steel sets or the rock bolts. In case if the requirement is such that you need more than one support system for a single application, then we need to go for the combined support system, and therefore we need to obtain the available support curve for such a system. So, in that case, what exactly is the data which is needed? So, we will need the stiffness and the support pressure, maximum support pressure for all the support system which are needed to be installed. So, let us list all the input data down here. The first one in the list is K1, which is the support stiffness of system 1. Then we have PS max 1, which is the maximum support pressure for system 1. We have K2 similarly, so this is going to be the support stiffness of system 2, and we have PS max 2, that is maximum support pressure for the second system. Then we will also need UIO, which is the initial tunnel deformation before the installation of the support systems. Now, here if you recall our discussion earlier also I mentioned, so again here I am emphasizing that both the support systems should be installed at the same time. So, here we need to take a note of the fact that the two support systems are assumed to be installed at the same time, and they also respond simultaneously to the deformations. So, that is also an assumption which is involved, and to start responding to tunnel deformation simultaneously. So, this is what you need to keep in mind as the note. What should be the calculation response for the available support curve? Let us try to see. In case of the combined support system, here you need to provide some logic. If you recall, I discussed with you that if you have the shotcrete and the steel sets, of course, the deformation for the shotcrete will be more as compared to that of the steel set, and the stiffness of the steel set is much larger than the stiffness of the shotcrete. So, how to choose that which one will be governing in case if you have the combined support system where you have shotcrete as well as the steel set. So, here we are going to write a generalized algorithm to obtain the available support curve in case of the combined support system. So, what all going to be the calculation sequence? Let us see. This is going to be first as u max 1. We will find out which is going to be equal to Ri into Ps max 1 divided by K1. So, you see that here we are using the input data for the first support system, and we are trying to find out that what is going to be the maximum deformation knowing K1 and Ps max 1 along with the tunnel radius. Then we will find out for the second system, which is u max 2. This we can write as Ri into Ps max 2 divided by K2. If these two are combined, what will happen? We will have u12 which is equal to Ri into Pi divided by K1 plus K2. So, this is how we can find out the deformation for the first system, second system and the combined one. The question is, how should we get the available support curve for the combined support system? So, here we need to provide a logic now, that is for u12 less than u max 1 and this is also less than u max 2. That means out of these three deformation, u12 is the minimum. So, in that case, how are we going to find out the support curve? That will be ui upon ri. This is going to be equal to uio upon ri plus pi upon k1 plus k2. Since here u12 is minimum, so the stiffness of the combined support system is going to govern the available support curve, and therefore, instead of k, here we are writing k1 plus k2. But if this is not the condition satisfying, then how should we go ahead? So, for such thing, we need to take another logic, that is for u12 more than u max 1, but this is less than u max 2. So, this means what? Out of the three deformation values, that is u max 1, u max 2 and u12, which one is the minimum? It is u max 1 which is the minimum. So, in this case, which support system will govern? It will be the system 1. So, in this case here you will have u max 1 attained the first. So, this will be attained first, and therefore, we can say that the deformation of system 1 will govern Ps max of the combined support system. So, therefore, we can write that Ps max 1 2 will be equal to u max 1 into k1 plus k2 divided by Ri, because u max 1 is minimum. So, the deformation of the system 1 will govern the available maximum support pressure, and therefore, for the combined support system, this maximum support pressure, which is PS max 1 2, will be equal to U max 1 into K1 plus K2 by Ri. In case if you have U max 2 as the minimum deformation out of U max 1, U max 2 and U12, then what will happen? So, we have the next step in this situation, that is for U12 greater than U max 2 and less than U max 1. So, in this case, this will be attained first. Why? Because it is least. In all the three situations, this is the least one, and therefore, we will have PS max 1 2 as U max 2 into K1 plus K2 divided by Ri. So, this is how you can find out the maximum support pressure in case if you have the combined support system. Most of the time it is only two type of the support system which are combined. Now, what about the allowance of dead weight of the broken rock? I discussed with you that when you excavate, what happens to the surrounding rock mass is that in the roof portion there is going to be some zone of the broken rock mass whose dead weight becomes very important as far as GRC for the roof is concerned and also for the floor. But as far as the side walls are concerned, their GRC will not be affected that significantly with the help or by this dead weight of the broken rock. And therefore, I mentioned to you that first we carry out the analysis without considering the dead weight of the broken rock, and then later on we will incorporate this. So, how it is done? Here we are going to discuss. So, the required support line which were defined by these equations Ui is equal to RIO 1 minus and this expression, and Ui by RIO equal to 1 plus nu by E P naught minus Pi. So, these equations we have learnt already in the earlier classes. So, these two equations can be considered to represent the behavior of the side walls of the tunnel, because the stresses and the deformation in the side walls they are not influenced to any extent by the dead weight of the broken rock which is surrounding the tunnel. But coming to the roof and the floor portion of the tunnel, we cannot say the similar thing. So, there we need to provide the allowance for the dead weight of broken rock. So, in order to allow for the dead weight of the broken rock in the roof and the floor of the tunnel. So, you see that if this is what is the tunnel, so this portion will be considered as the side walls, this is roof portion and this is the floor portion, or we call it as invert as well. So, in this case what we do is we have already obtained the support pressure without the allowance for the dead weight of the broken rock. So, if it is the roof portion, we will increase that support pressure Pi which we have obtained without the dead weight, and for the floor we reduce the support pressure that we have obtained. So, how much increase or how much reduction should be done is gamma r into Re minus Ri should be added or subtracted to the support pressure that we have obtained without the allowance for the dead weight of the broken rock with respect to roof and the floor respectively, where this gamma r represents the unit weight of the broken rock. You need to keep this in mind that this particular correction should be done only after the required support line for the weightless condition has been calculated. So, repeatedly I have been telling you that first we do not consider the dead weight of the broken rock in the analysis. Once we do it without the weight of the broken rock, and then we incorporate indirectly in this particular manner to take care of the GRC for the roof and for the floor. So, when we do this, this method more or less provides us the reasonable estimate of the effect of the weight of broken rock, although it is a very gross simplification, but for all practical purposes it gives us the reasonable estimate of the effect with reference to the allowance of dead weight of the broken rock for GRC of the roof and the floor. So, this finishes our discussion on Ladani's elastoplastic analysis for the rock mass tunnel support interaction. What we will do is, in the next class we will take the help of these calculation sequence, and then we will try to solve few examples of different support systems, and also we will try to see how we can determine the ground response curve for roof, side walls and the floor of the tunnel. This example will give you the idea how to attempt to any problem related to the ground response curve and the support reaction curve. Thank you very much.